Hello everyone, this is lecture 13 of ComSci 141, Properties of Context-Free Languages. In the previous video, we discussed equivalence of PDA and CFG. We showed how to convert from PDA by final state to PDA by empty stack and vice versa. We also showed how to convert a given CFG to its equivalent PDA and how to convert a given PDA to its equivalent CFG such that they accept the same language. We are now on the last topic for context-free languages in pushdown automata, which would be the properties of context-free languages. In today's video, we will discuss the decision algorithms, closure properties, and the pumping lemma for context-free languages. So, recall from last time when we already had the properties of regular languages, right? So we also discussed the decision algorithms and the closure properties. So for decision algorithms, remember that they are algorithms that tell us whether or not some property holds true, okay? And then for closure properties, these are operations that produces the output that's in the same class as operands. So that means that if you're given two context-free languages, if you apply that operation, it will always produce a context-free language as well. Okay? And remember that we need to use formal representation for decision and the closure properties. So, in the case of regular languages, we use the finite automata and regular expressions because these were the formal representations, right? We can't just use the English description of the language. We have to write the finite automata or the regular expression representation of the language. So for the context-free languages, we would have to write either the pushdown automata or the context-free grammar as the formal representation when we use this to prove the decision and closure properties of the language. So remember from last time that the decision properties for regular languages were as follows. So we had the membership. We could test for membership of a string in the language using the DFAs. We'll just simulate how the DFA will act given the input string, and then if it reaches a final state, then it's accepted. And then for emptiness, also for DFA, we just check if the start state can reach any of the final states, because if not, then none of the strings would be accepted, right? For infiniteness, we could check either the DFA for a loop, right? Because then you could take that as many times and then it would be infinite. Or for the regular expression if there are closures. For the equivalence and containment, or the containment, or if it's a subset, then it's we use the product DFA, right? So is L a subset of M, or is L equal to M? So we use the product DFA for that, remember? Now, for the context-free languages, on the other hand, these are the decision properties. So first, membership. So we still have membership as a decision property. So it answers the question, is the string W part of the language? Next is emptiness. So is the language L empty? We also have infiniteness. So is the language infinite? Does it have an infinite number of strings in the language? And that's it. Okay, so these are the three decision properties for context-free languages. So note that there are no algorithms to decide for equivalence if they are disjoint, meaning they don't have any common strings, right? So given two languages, are they disjoint? Ambiguity of the language and inherent ambiguity. Is it ambiguous? Like if you draw up a parse tree of one string, will it produce two parse trees, right? Or two leftmost, rightmost derivations? So yeah, there are no algorithms to decide these properties for all context-free languages in general. There could be some algorithms that decide it for like a few that will work for a few context-free languages, but it doesn't really work for any context-free languages. So it cannot cover everything. Okay, so only these three have algorithms to actually decide if this property holds true for all context-free languages. Okay? So let's start with the first one, which is emptiness. So again, we ask, is the context-free language empty? Are there no strings in the language? So what we'll use here for our formal representation is the context-free grammar. And the first thing that we'll do is we'll remove variables that don't derive terminal strings. Because if they don't derive terminal strings, then of course they cannot produce terminals, right? So let's simplify the grammar by removing variables that don't derive terminal strings. And if the start symbol is removed, that means that the CFL is empty. Why is that? Because if the start symbol is removed, remember that all of our derivations for the grammar starts with the start symbol, right? Starts with this one. But if the start symbol does not derive any terminal strings, then that means that there are no strings in our grammar. Because if our start symbol cannot derive any terminal strings, then no one can. Okay, or no variable can. Okay. So yeah, that's how we check if the language is empty for context-free languages. Next is infiniteness. Is the given language infinite? So for this one, we will use the simplified CFG. So remember the 4 steps for simplification, right? Like you remove the unit productions, you remove the useless symbols, you remove the epsilon productions, and so on. So yeah, after you have simplified the CFG, so we can now assume that it has no unit productions, epsilon productions, and useless symbols. What we will do is we will construct a directed graph where nodes are the variables of the CFG, and if there is a production of the form like ax by, so we will add an edge, a directed edge from A to B. Okay, so if the variable A derives B as in one of its productions, okay, we will add an edge from A to B. Okay, so we'll form like a directed graph. And if that graph has a cycle, then the language is infinite, because of course you can take that cycle as many times as you want, and it would produce infinite number of strings, right? So let's see some examples. So for this one, well, there's only one variable, so that's s, and s goes to s because of this production. So you have a self loop here, and so this is infinite because there is a loop here. Okay, there's a loop here, and that means that well, you can take this as many times as you want. Okay, next, how about this one? So we have 3 variables, s, a, and b, and then s goes to a and b, so there's a directed edge from s to a, s to b, and then from a it goes to a as well, and b goes to b as well. So this is also infinite because of the self loops. Okay, next, how about this one? Okay, this is a little bit more complicated, so let's try. We have 4 variables, so that's a, b, c, and d, and then with s, and then s goes to a and c, also goes to a and b, b and d, and b and a. So it's connected to all 4. Now for a, it doesn't connect with any other variable because it only has terminals. The same with b, right? So we don't add any more edges for b, a and b. Now for c, it's connected to both s and b. So c is connected to s, okay, and connected to b, right? And then for d, it's connected to s and a. So d is connected to s and then connected to a. Okay, so this is the final graph. Now, is there a loop here? Well, yes, there is, because of this one. Okay, so this one is the loop here, and here's another loop, right? So you can take as many cycles here as you want, and then it would make the language infinite. Okay, so yeah, this is also infinite. Okay, so that is how you determine if the language of the or the given context-free language is infinite or not. So you use the CFG and the simplified CFG and create the directed graph and find out if there's a loop in the graph. Okay. Next is membership. Is the string W part of the language? Okay, so you're testing for membership of the string. So remember that for the regular language, what we did was we simulated the DFA given the input string and accept it if it ends up in the final state. So we can do this because it's deterministic. However, for our context-free language, if we do this for the pushdown automata, the pushdown automata is by default non-deterministic, right? It can go to many different transitions on a single like setting. So there are options as to which transition you can go to since it's non-deterministic, and because of that, it may take exponential time to simulate. Okay, if we use the pushdown automata, the non-deterministic pushdown automata. So that's why we cannot use this just like what we did in regular language. Like in regular language, we used DFA, but this worked because it was deterministic. We knew where to go to given this transition. But since PDA is non-deterministic, then there are many possible choices that we could take, and that would take exponential time. Okay, which is bad. Takes too long. So what we will do is we will use instead the context-free grammar. And first, we will convert it to its Chomsky normal form to simplify it. Okay, and then if we use brute force, then we can explore all possible derivations of the string given the Chomsky normal form and check if the string is derived out of one of those possible derivations, right? So if you brute force it, just check all possible derivations. But again, take note, the problem here is that there are way too many possible derivations. Okay, it will take exponential time. So for example, in here, this is already converted into its Chomsky normal form, right? Because it has either two variables or just one terminal. So if we try to derive the input string here, so from A, okay, so from A, we could either go to, this could either be BC or AB because we don't know which one of them will yield this string, right? Then from BC, from B, this could be AA. Then from C, this could be CB. But then A again could either be BC or AB. Then this A could also be BC or AB, and so on. And then this A could again be BC or AB. This B could be AA, AA, and so on. So you'll notice that because of the A here, this will result in way too many branches. Okay, there's way too many possible derivations of the string. So if we do this, it will take too much time. Okay, so in the Chomsky normal form, at each step, at least the variable can be replaced by two variables, right? So this one variable can turn into two each time. Okay, so at the worst case, it could take us big O of 2 raised to n, or exponential time, where n is the length of the input string. And well, if you think about the number of possible derivations given the length of the string, so if you start with 4, that would be 2 raised to 4, so only 16 possible derivations. But if the length of string was 10, that would be 2 raised to 10, or about 1000 possible derivations. If it was 20, length of string is 20, that would be 2 raised to 20, or about 1 million derivations. And then if the string length was 30, 2 raised to 30 is about 1 billion possible derivations, right? So from 4 to 10 to 20 to 30, it went from 16 to 1000 to 1 million to 1 billion. And well, that escalated quickly, right? So you don't want to use the brute force approach. Okay? Well, fortunately, there are polynomial time algorithms that exist to test for the membership. So we have, for example, the CYK algorithm, which takes O of n cube. So at least this is in polynomial time. And then we also have the earliest method, which is O of n cube in general. But if the grammar is unambiguous, it could even be faster. It could run in O of n squared. Okay, so again, take note that n here denotes the length of the input string. So the CYK algorithm, just to give you a quick background, was created by John Koch, Daniel Younger, and T. Kasami. So that's why it's CYK. And it's basically a bottom-up parsing algorithm. So we discussed this, right, before when we talked about parse trees. So bottom-up starts from the input string itself, and then go work upwards to build the previous intentional forms until you get the start symbol, or the start symbol. So it's a bottom-up parsing algorithm, and it uses dynamic programming. Okay, so dynamic programming is of course you're familiar with this. It's a algorithm design paradigm wherein you use the past. You remember the past answers to previous sub problems so that you don't have to recompute it. So it also uses like a tabular method, dynamic programming. And then for Early's method, it was created by J. Early. This one, on the other hand, is a top-down parsing algorithm. So start from the top, starts from the start symbol, and then tries to derive the string, and then doing backtracking if it makes a mistake until it derives the given string. So it's top-down parsing and also uses dynamic programming. Okay, that's why both of them are in n cube, because they will create like a three-dimensional array, perhaps. Okay, so we won't use the brute force approach for testing the membership because it will just take exponential time. But fortunately, there are polynomial time algorithms that will test for membership. Okay. Okay, so that's it for the decision properties. Now let's move on to the closure properties of the context-free languages. So remember that for closure operations or closure properties, you're given two languages of the same class, and applying the operation will always result in the same language class. So in this case, if you're given two context-free languages, applying these operations will always result in a context-free language as well. So what are these operations? So we have the union, concatenation, Kleene closure, reversal, and homomorphism. So you're familiar with these operations from the closure properties of regular languages as well, right? So let's see. So for union, if L and M are context-free languages, then the union L union M is also a context-free language. So for the proof, we will use the CFG, the grammar of the two languages. So let G and H be the context-free grammars of L and M. And the assumption is that they have no common variables. So if they have common variables, then rename them so that there won't be any conflict. Okay? And to create the grammar, the context-free grammar for L union M, assuming that S sub G and S sub H are the start symbols of the two grammars, then we will just create a new start symbol, S, and we add this production. S could be SG or SH. So that means that S could derive the strings in the grammar of G or the strings in the grammar of H. Okay? So that's it. That's already the this is already the CFG for L union M. It already derives all strings in L and in M, given that the grammar was G and H respectively. Okay, and since it has a context-free grammar, then we are sure that it's also context-free. Okay. Okay. Now for concatenation, we will do the same thing. So if L and M are context-free languages, then the concatenation LM is also context-free. So we'll still use the context-free grammars of the two languages to prove that concatenating them would also produce a context-free language. So let G and H be the CFGs of L and M respectively. And again, the assumption is that they have no common variables. So we can create the CFG for LM by doing this. So assuming that SG and SH are the start symbols of the two grammars, then we'll just create a new start symbol and have this production. So S is equal to SGSH. So you just concatenated the two start symbols of the two grammars, and that will create the CFG for LM. So this variable will produce strings that start with string from G and end with strings from H, and then you concatenate them together. And since we've created a CFG for LM, then we are sure that it's also a context-free language. Okay. Next, we have Kleene Closure. If L is context-free, then L star is also context-free. So we'll still use the grammar of L. Let's call it G. Okay, and let SG be the start symbol. So we'll just make another CFG starting with the start symbol S and add this production. So since it's L star, so it's zero or more copies of the same language, right? So of the same string. So S could be epsilon, so there could be an empty string, or you could repeat it by having SG and then add more S. So you can always add more SGs here, and then if you're done, S can just be replaced here with epsilon. Okay, so this is the production for Kleene Closure. And since we have created a CFG, then we're sure that it's a context-free language. For reversal, same thing. So if L is context-free, the reversal of L is also context-free. So we will use the grammar still, CFG, of the language. So if G is the context-free grammar of L, we will form the context-free grammar of the reversal by reversing the right side of each production. Okay, so what do you mean by this? So let's say that this is your given CFG, OS1 or O1. For the reversal of this language, then we will just reverse all productions here on the right hand side. So instead of OS1, it becomes 1SO. Instead of 01, it becomes 10. Okay, and since this is a valid CFG, then we are sure that the reversal is also context-free language. Okay, so pretty simple, right? And finally, we have the homomorphism, which, if you remember, is like a mapping or translation function. So for example, if the homomorphism maps 0 to AB and 1 to epsilon, then if you have the homomorphism of the string 0, 1, 0, 1, 0, then the zeros here would be replaced by AB, and then the ones would be replaced by epsilon. So that's why we have the AB, AB, AB here, because of the 3 zeros, and then the ones became epsilon, so they disappeared. Okay, so we've already seen this from the regular languages, right? So if the language is context-free, the homomorphism of the language is also context-free. And it's pretty straightforward to construct the CFG for the homomorphism. Just replace each terminal symbol A by the homomorphism of A in the original context-free grammar. Okay? So for example, if you have this grammar, OS1 or O1, and then the homomorphism is for 0, you replace it with AB, then for 1, you replace it with C. So the homomorphism's context-free grammar would look like this. So the zeros would be replaced with AB, so it became AB here, and then the 1 would be replaced with C. So that's why this became ABSC and then ABC. Okay? So pretty straightforward also. So just replace it with the homomorphism, and then you will get a valid context-free grammar. And since you got a CFG, then we are sure that the homomorphism is also a context-free language. Okay? So that's it for the closure properties. Now, we also saw some properties before in the regular language, like the intersection and difference, that were closure properties in regular languages. However, in CFL, in context-free languages, they are non-closure properties. So let me show you why. So for intersection, I'll show you an example. So we know that this language, 0n, 1n, 2n, is not context-free. Why is that? Because remember that for context-free languages, it can only count two things. But here, you should count the number of zeros, the number of ones, and the number of twos, and make sure that they are equal. So you're actually counting three things. So this is not context-free. Okay? So, yeah. And then, let's see another language. How about this one? Is this context-free or not? So you have 0n, 1n, 2i, wherein n could be greater than or equal to 1, and then I could be greater than or equal to 1. So think about it for a second. Is this context-free or not? Well, this one is actually context-free. Now, why is that? So although we have three things here, like 0n, 1n, 2i, we're actually counting only two things. We're interested in counting only two things. And that is the number of zeros and the number of ones. And making sure that they are equal. Because the number of zeros must be equal to the number of ones, right? You have 0n, 1n. But now, how about for 2? Well, 2 has the number I, or yeah, it has the exponent I. So I could be any number from 1 onwards. So you don't really care about the number of 2's for as long as the number of zeros and ones are equal. Okay, so this is still context free. And in fact, I will show you a grammar for this later on to prove that this is in fact context free. And now, how about this one, the third language? OI, 1n, 2n. Is this context free or not? Well, this is also context free for the same reason. Now, even though we still have three things here, zeros, ones, and twos, we're still only counting two things in this case. So that is the number of ones and the number of twos, and making sure that they are equal. So 1n, 2n, right? For the number of zeros, we don't really care how many zeros there are. So it could be any number of zeros that's greater than 1. So notice that L2 and L3 are context free, whereas L1 is not context free. Okay? So for L2, we said that this is context free, ON1 and 2i. This is the equivalent context free grammar. So S is equal to AB, wherein A could be 0A1 or 01, and this will make sure that there's an equal number of zeros and ones, right? Now for B, you just add any number of twos, right? It could be 2 by itself, or you add more twos by repeating B. 2B, 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 and so on. Okay? For L3, it's the opposite. A is now the one that's being repeated as many times, like for 0. So 0 could be 1 or more times. So you have A is equal to 0 or 0A. So you can repeat 0 as many times as you want. Whereas for B here, this would control the number of ones and twos, and making sure that there's an equal number of ones and twos. So every time you have a 1, there's a pair 2 here. So 1 and 2. And then you can add more inside it. So you can nest the 1, 2's inside to make sure that they have equal number. So L2 and L3 had context-free grammar, so they are context-free languages for sure. Now, let me ask you this question. What is the intersection of the two languages? So what is the intersection of ON1N 2I and OI1N 2N? What is their common string? Well, their common string is if it's ON1N 2N, right? Because if N here becomes I and N here becomes I here, then that is ON1N 2N. But ON1N 2N is actually the L1, right? Because we saw that L1 was the ON1 and 2N, which we know is not context-free. Okay? So the intersection of two context-free languages resulted in a non-context-free language. That is why intersection is not a closure property because it did not produce a context-free language in this case. Okay? So, yeah. And for difference naman, it's just an extension of intersection. So, if the language class is closed under difference, then it's also closed under intersection and vice versa. But since we know that the context-free languages are not closed under intersection, then it's also not closed under difference because you can express intersection as a difference, like L minus M, right? So L minus M are the things that are not in L that are in M, and then you subtract that from the things in L, so you have the common items in L and M. Okay, so CFL is not closed under intersection, so it's also not closed under difference. Okay, so it's just an extension. Now, why did this work for the regular language intersection? So, regular languages are closed under intersection, and the way that we did that, or we proved that, was by using product DFA, right? Remember the product DFA, given two DFAs, you basically created the product DFA by running them in parallel. So, you run two DFAs in parallel. Now, why can't we do this for context-free languages? Well, running two PDAs in parallel, if you run two push-down automatas, it will require two stacks, right? So one PDA has a epsilon NFA plus a stack, and then the other PDA also has a stack. So if you run two PDAs, you'll have two stacks. So if you create the product PDA, you can't have two stacks, right? Because it can only have one stack. So the product PDA with two stacks cannot exist. That's why we cannot use the PDA in proving intersection. However, if you were to take the intersection of a context-free language and a regular language, you can do so. Okay? A CFL intersection regular language will always be a context-free language. Why is that? Well, the idea is you run the DFA in parallel with the PDA. And this time you can do that because DFA plus PDA only has one stack, which is possible. Okay? So you can do that. So you'll run them in parallel and you accept the string if both the PDA and the DFA accepts. Okay? But if it's CFL intersection CFL, then we're not it always doesn't it doesn't always result in a context-free language. Okay? Some of them could result in a CFL, but not all. And the important thing for closure properties is that it should always result in that same language class. Okay? But given that we showed one counter example of it not working, then it's not closed under that operation anymore. Okay? So that is closure properties. Now, we are ready to go to the last part of the properties of context-free languages, which is the pumping lemma for context-free languages. So, it's the pumping lemma again. If you had a problem or if you had trouble understanding the pumping lemma for regular languages, well, it's back. So, you have to dig deep, I guess, or really try hard to understand this one. But it's really intuitive if you have already understood the first pumping lemma, which was for regular languages. Okay? So let's see. So again, the pumping lemma is used to show that certain languages are not part of a language class. Okay? So for pumping lemma for regular languages, we used it to show that some languages are not regular. So for the pumping lemma for context-free languages, we will use it to show some languages are not context-free. Okay? So remember this from the pumping lemma for regular languages. For every regular language L, there's an integer n greater than equal to 1, such that for every string W that's part of the language that's sufficiently long, so it's greater than or equal to n in length, we can divide or write W in three parts, x, y, z, such that the conditions are met. So the length of xy is less than or equal to n, the length of y is greater than or equal to 1, and if you have x, y, k, if you pump y, okay, k times, where k could be greater than or equal to 0, so it could be 0 times, 2 times, 3 times, and so on, it would still be part of the language. Okay? And the explanation for that was, if you're given any sufficiently long string accepted by the regular language, we can find a non-empty substring, which is y, near the beginning of the string that may be pumped or repeated as many times as we want, and the resulting string will still be accepted by the regular language, right? So that was the idea for the regular language pumping lemma. We pumped one substring, which was y, and by doing so, the resulting string will still be part of the language. So how about for the context-free language na pumping lemma? So the CFL pumping lemma applies to all context-free languages. So it's used to formally prove that a language is not context-free. So here is the pumping lemma for context-free languages. So let's read it slowly. For every context-free language L, okay, there is an integer n greater than 1, such that for every string z that's part of the language, where z is greater than or equal to n in length, okay, so it's sufficiently long, we can write z this time into 5 parts, u, v, w, x, y, such that the following conditions are met. So previously in the pumping lemma for regular languages, we only divided it into 3, right? X, y, and z. This time, we'll divide it into 5. So u, v, w, x, y. Now, what are the conditions? The length of vwx should be less than or equal to n. So this part here, vwx, the one in the middle, should not exceed the length of n. Vx, the length of v and x, should be greater than or equal to 1. Okay, and if you pump v and x with k, okay, it should still be part of the language for any k greater than or equal to 0. Okay, so the difference here is that in the pumping lemma for CFL, we are now pumping in 2 places, in v and x. Earlier, it was just in y, right, in the middle for regular language. This time, we are pumping in v and in x. Okay, so what does this all mean? So you're given any sufficiently long string z. So it's sufficiently long because the length is greater than or equal to n, and it's also accepted by the language, right? We can find 2 substrings, v and x. One can be empty, but not both. So this is the second condition, right? Length of vx is greater than or equal to 1. So if the length of vx is greater than or equal to 1, it could be that like v is like of length 1, so it could be like a, and then x could be epsilon, or it could be that v is epsilon, x is the a, could be length 1, right? So that's possible because the length of vx here is 1, length of vx here is 1, and then it could be more than that, right? Because it's greater than or equal to 1. But it's not possible to have them both as epsilon. Okay, this is not possible because the length should be greater than or equal to 1. Okay, and then the v and x should be close together such that they are not more than n spaces apart. So the length of vwx should be less than or equal to n. Okay, and then they should be close together, and we need to pump and repeat them in tandem. So you have the vk, xk here, and the pumped string is still part of the context-free language. So it's still in the language, and this could work for any k greater than or equal to 0. Okay, so now how will we use this to prove languages to be non-context free? Well, we'll use the same approach as we did in the regular languages. So to prove that a language is not context free, we will use proof by contradiction. Assume that the language is context free, and then show that this eventually leads to a contradiction using the conditions in the pumping lemma for context free languages. And then this will prove that the language is indeed not context free. Okay, so we will show 3 examples and use the pumping lemma to prove that they are indeed not context-free languages. So we will use this for the language OM1, OM1, OM, OM1, M2M. So this was similar to the example that we had earlier, right? And then OM, where M is a perfect square. Okay, so we'll go through each one and see how to use the pumping lemma for CFL to prove that they are not context free. Okay, so first let's look at how to prove this language OM1 OM is not context free using the pumping lemma. So this is not context free because we cannot match more than one pair. So take note that the number of zeros in these three places has to match, right? So the number of zeros here has to match the number of zeros here, has to match the number of zeros here. And then they have the one dividers in between to denote where it should stop, right? And since in the intuition for CFL is that it can only count two things, we can't do that here because we have to count in three places, right? So this is not context free. But we will show proof using pumping lemma to make it more formal. So the first thing that we'll do is we'll assume that this language is context free. And because of that, well, the pumping lemma for CFL will hold true for this language. So first thing that we'll do is we will choose a sufficiently long string, Z. Okay? And the length should be greater than or equal to n. So we will choose the string 0n 1 0n 1 0n. And this is valid because this is part of the language, right? This is 0m1 and 0m1 0m1 0m where m is equal to n, and the length of z is greater than or equal to n because what is the length of this string? Well, you have n times 3 because of the 0n 1 0n 1 0n. So you have n times 3 here because of the 3 n's here, and then the plus 2 here. So that's 3n plus 2, which is of course greater than n. The plus 2 here, make sure of that. Okay, so this is a valid string to use. And then because it follows the pumping lemma, we can write the z as uvwxy such that it follows the two conditions. The length of vwx should be less than or equal to n, and vx should be greater than or equal to 1. Okay, so if z here, which was 0n 1 0n 1 0n, if this could be divided into u v w x y, there are only two cases that could happen, right? So we are interested in v and x because v and x are the ones that we will pump, right? Remember? So remember that we will pump this later with k because these are the parts that we need to pump, right? V and x. So these two parts are interesting because these are the parts that will pump. So two cases will exist. Either v and k will have no zeros, or not v and k, vx has no zeros, or vx has at least 1 0. So it either has no zeros or at least 1, right? So those are the two cases. So what will happen if it has no zeros? Then that means that v and x are like this, because the only v and x can only be taken from this 2 here. Okay, because the only non-zero symbols in the string are this one and this one, right? So if it has no zeros, then you can only take v and x from either the red one or the green one. So take note that there are n zeros that separate them. Okay, so it can't possibly be that okay, so remember that we had z is equal to u v w x y. Okay, and the length of VWX cannot exceed n, and then Vx has to be greater than or equal to 1. Remember? So if the configuration was that it was 0n1, 0n1, 0n, if it was Vx like this, if both V and X were on the ones, well, this cannot happen because that would make W become this 0n here, right? But the length of VWX in this case would be, what would be the length of VWX? Well, V is a 1, W is a 0n, and X is a 1, so that would be 1 plus 1 plus n0, so that would be n plus 2. And that is actually greater than n, so that would violate this one, right? So both V and X cannot be 1s. Only one of them can be a 1. Does that make sense? Because there are n zeros that separate them. So it's either V is an epsilon and X is a 1, and then there could be zeros here. That would be the W, right? Yeah. Or even U could take some of the zeros here, and then this is just n minus 1, because the length of VWX has to cannot exceed n, right? So if this is the configuration, well, what will happen here? V's length is 0, W's length is n minus 1, X's length is 1, so this will length of n, right? So this is possible. Or another configuration would have to be, what if V was the 1, so W would have to be 0 n minus 1, and then X would have to be epsilon, right? So that's the only way that we could have V and X if there are no zeros in V and X. Okay, so this is still possible because, well, you have 1 here, n minus 1 here, that's a total of n, and it will not exceed the length of n. Okay, so we really only have two cases here. Either because of the condition that it can't exceed n. So the two cases are either V is equal to 1 and X is epsilon, right, as I showed you earlier, or X is 1 and V is epsilon. But they can't both be 1 because, again, there are n zeros that separate them. Okay, if they are both 1s, if this one is V and this is X, and then this would become W, the length of VWX in this case would have to be 1 plus n plus 1, which is n plus 2, and that exceeds n, which is not possible, right? Because length of VWX has to be less than or equal to n. So because of that, either only only V is 1 or only X is 1. Okay, so if V is 1 and X is epsilon, what will happen? If we pump this down using K0, so what will happen? This will become V0, X0, so this will become epsilon, right? It will become empty strings. So it will only become UWY, right? But the VX already has the 1 here because of this one. So UWY will have the remaining 1. Okay? So UWY only has 1, and that is not part of the language because the language needs to have 2 1s. This one and this one. But since we pumped it down and V's 1 got deleted because it became epsilon, then the remaining string UWY only has 1, and so it's not part of the language. Does that make sense? So if this was the breakdown, for example, if this was 0 n 1 0 maybe n minus 1 and then epsilon, and then another 0 for the 0n here, and then 1, and then 0n. So maybe this one, I will call this the v. This is the v is equal to 1 here. This x here, this epsilon is the x, and then this one here is the w. Okay, and this is valid because the length here is length of vwx is equal to n. Okay, so that means that the remaining one here is u, and the remaining one here is y. Okay, but if you pump this down, okay, I'll make this red. If you pump this down, if v0 and x0, that means that v becomes epsilon, x becomes epsilon. So if this becomes epsilon, so we'll remove this one, and x becomes epsilon as well. So the remaining string is only this one, u, w, and y. So the remaining string was 0n, so u, w, y is equal to 0n, 0n minus 1, and then plus the 0 here, so it's actually 0, 1, 0n. So if we combine these two, it is 0n, 0n, 1, 0n. So this one is not part of the language. Sorry. Not part of the language because it has to have this one here, which was removed. Right? So, it's not part of the language, so it's a contradiction. Okay? Next, what if x was the one that has the 1? So, with all these ones here, it might become confusing, but just try to imagine what I'm talking about. So, if this was the case, okay, before we pump down, let's try to imagine how this was broken down. So, 0, n, so v, there's an epsilon here. This is for v, right? And then x is a 1. Okay? So, the w here, oh sorry, I should have switched that one. 1 should be on top, and then x should be here. So w should be here, and it can only have 0, ilan ba? N minus 1, I guess. Yeah, only n minus 1 because then the length of this vwx's length is equal to n minus 1 plus 1. That would be n, which is okay. So what would be the u? Well, since this one is lacking a 0, there should be a 0 here and a 1 here. Right? So that's 0n, 1, 0n, 1, and then 0n here. So this would have been the u, and this would have been the y. Okay? So that's the breakdown. Now, if we do the same thing with pump down, if we use k is equal to 0, right? Because take note, k could be greater than or equal to 0, right? So if we pump down, what will happen is v0 and x0 will become epsilon. So what will remain is still uwy. Okay? So if we pump down, maybe green this time. If we pump down, what will happen? Okay, so v0 epsilon and x0 is also epsilon. So we will remove the v here, we'll remove this one, and we will also remove the x, right? We'll remove this one. So what remained would be this u here, this w here, and this y here. So uwy is actually 0n, 1, 0, 0n minus 1, and 0n. So if we simplify that, if we combine these two, that would be 0n1, 0n, 0n. And again, this is still not part of the language because it's missing the 1 here. Right? It should have this 1. So, this is not part of the language. Okay, so it's a contradiction. So since the Vx already has the 1, then the remaining uwy, it only has 1 as well. So it's not part of the language. So it's a contradiction. Okay, so for both cases, we show that it's a contradiction. But is that it? Well, no. That's only the first case. That is only if... Okay, so what is this first case? The first case is if Vx has no zeros. But we still have the second case. And that is, what if Vx has a 0? Okay? Well, if Vx has at least 1 0, it could take it either from this green zeros, from the red zeros, or from the yellow zeros, right? So, and remember that VWX cannot exceed the length of n. So Vx cannot span all 3 blocks. Why is that? Well, okay. Let's see. Okay, so I'll draw that one here. Have the 0n, and then the 0n here, and then the 0n here. Maybe not that one. Okay, maybe this one. Okay, then we'll add the ones. Okay, so if we had v and x, like for example, if v started here, if one possibility is vx could both be here in the 0n, right? Because that's possible, because the length of VWX in that case would not exceed n, right? That's one possibility. Another possibility is the v and x could be all here, right? In the second 0n, that's also possible, because then the length of VWX would be less than or equal to n, because it's inside this n zeros. And again, it could also be here, right? But another possibility is that the v could be here in 0n, and the x could be could it be here? Well, yes, it's possible. It could be here. Like, how would that happen? So for example, if you had the 0 0 0 1 0 0 0 1 0 0 0, so assuming that n is equal to 3, it could be that like Vx is both here in the 0 0 0, could be that Vx could be here in the second 0 0 0, or Vx could be here in the third 0 0 0. But it's also possible that we start with V here and end with X here, right? Or we start with V here and end with X here. But however, it cannot span all 3. Like, it cannot start at V on the first 0 block and X is in the third block. Why is that? Because there are n zeros that separate them. So that means that you cannot have the length of VWX less than or equal to n if that's the case, that you started at the first block and ended at the last block, because there's 1 that separates them, and then there are n zeros that separate them as well. So that's already n plus 2, and that's already more than the limit for the length, right? So there are 5 possibilities. Either Vx is here, 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 or span 2 blocks, or span 2 blocks here. Okay, so yeah, so in the first case, Vx could be in the green 0n. Second case, it could be in the red 0n. Third case, it could be in the yellow 0n. And then the fourth case is it's in between these two. Okay, and that's possible because you can start V at the last part of this 0n, and then X could be starting at the first part. Okay, And then it could also be between this 0n and this 0n. Okay? But in all cases, we need to show that they all end in a contradiction. Okay? And that is how you use the pumping lemma to prove it wrong. It doesn't have to mean that you just assume that maybe it's here or maybe it's here. No, you have to show it for all possibilities. Okay? That makes your proof valid. So, if the Vx was in the green part of 0n, if we pump this up, if we pump up the Vx in green, then the numbers of zeros in the green block will have more zeros than the red block and the yellow block, right? Because we pumped it up. So that means that we'll add more zeros. So that means that the resulting string is not part of the language because it has more zeros here in green than in red and yellow. And then using the same argument, if it was in red, if we pump that up, then the number of zeros in red will have more than those in green and yellow. So also not part of the language. So it's the contradiction. And then for the yellow, if we pump that up, then the number of zeros in the yellow block will be more than the number of zeros in green and in red, right? So they won't have equal number of zeros, so it's not part of the language. Okay? And then for the fourth case, if it's between 0n and the green and the red, let's say that V is a 0 in green and X is a 0 in red. If we pump up, the number of zeros in green and red will be more than the one in yellow, because this will not be pumped up. Only the green and the red will be pumped up, right? So with number of zeros increasing here in green and red, there will be less zeros in yellow. So it's not equal. So it's still not part of the language. It's a contradiction as well. And then using the same argument, if we pump up red and yellow, then there will be less zeros in green, which makes them not equal. So it's also not part of the language. Okay? So in all 5 cases, we showed that it arrived in a contradiction. So in case 1, where it could have no zeros, we showed that for both cases, whether V was 1 or X was 1, both were contradictions. And then if it has a 0, we showed that for all the 5 cases, it could be in the green block, the red block, the yellow block, or in this block or in this block. But for all cases, it showed the contradiction. So therefore, we can prove that the language is not context-free. Okay? So it seems tedious, but you have to cover all bases. You have to cover all possibilities of what might happen, and you need to prove each one. Okay? So let's see another example. This time, it's the language 0m, 1m, 2m, where m is greater than or equal to 1. So the number of zeros, 1s, and 2s have to be equal, and they should be in order. So 0, 0, 0, 1, 1, 1, 2, 2, 2, something like that. So this is again not context-free because we are counting 3 things: the number of zeros, the number of 1s, and the number of 2s, and making sure that they are equal. Okay? So how do we prove it using the pumping lemma? So we'll assume again that this is context-free, and because of that, the pumping lemma should hold true for this language. So we'll choose a sufficiently long string, z. So we will choose, okay, zero n, 1 n, 2 n, because what is the length of z in this case? The length of z is n plus n plus n, which is 3n, which is greater than or equal to n, right? So yeah, and then it's also part of the language because of course it follows the 0m, 1m, 2m pattern. Now yeah, it's part of the language, and the length is greater than or equal to n. Okay, now of course we can write z as uvwxy, where it follows the 2 conditions. Length of vwx is less than or equal to n, and length of vx is greater than or equal to 1. And because vwx is greater than or equal to n, vx cannot span all 3 blocks as well. Okay, so why is that? So So more or less for the same reason as the one earlier that I showed you. So if this was 0n, 1n, 2n, and for illustration purposes, let me show n is equal to 3. So it will become 0, 0, 0, 1, 1, 1, 2, 2, 2. So there are actually 5 possibilities of where we could put v and x. And again, we're interested in vx because v and x are the ones that we pump, right? Now v and x, so since this is of length n, right? This is also of length n. This is also of length n. Vx could be here and here, right? And that is of length n. Or Vx could be here and here, inside the ones, or Vx could be here and here. But V and X could also start at 0 and end in 1. Could start at 1 and end in 2. Right? Just like what we saw in the earlier example. But what cannot happen is that it could start at maybe at 0 and end in 2. Well, this cannot happen. Why is that? Because in that case, even if we take if V was here and then X was here, and then this is W, so that means that the length of VWX in this case, well, V's length is 1, W's length this time is n because it spans all the ones, and then for X is 1, so this is actually n plus 2, which is greater than n, which cannot happen because it should be less than equal to n. Okay, so with that in mind, Vx cannot span all 3 blocks. Okay, so in this case we have 5 cases still, just similar to what we had previously in the first example. So Vx could be all zeros, all ones, all twos, or zeros and ones, or ones and twos. Okay, and the proof of this is pretty straightforward. So basically, if you have all zeros in Vx, if you pump up the Vx with all zeros, that means that there would be more zeros than ones and twos, right? Because V and X are all zeros, so there will be more zeros now if you pump up the zeros. Okay, so since there are more zeros than ones and twos, it's not part of the language, so it's a contradiction. If it was all ones, for the same reason, if we pump this up, then there will be more ones than zeros and twos. So this is also not part of the language, so it's a contradiction. And then if it's all twos, if we pump this up, then there will be more twos than zeros and ones, right? So that means that it's not part of the language, and it's also a contradiction. If it was zeros and ones, if we pump this up, then there will be more zeros and ones than twos. So it's the 2 that would have a lesser number, right, or lesser count. So this is still not part of the language because there's not an equal number of zeros and ones and twos. Okay, so it's a contradiction. And finally, if you have ones and twos, if you pump this up, then there will be more ones and twos than the number of zeros. Okay, because you did not pump up 0. So that means that it's not an equal number of zeros, ones, and twos, so it's not part of the language, and it's also a contradiction. So in all 5 cases, we showed that it arrives at a contradiction. Therefore, we have proven that the language 0M, 1M, 2M is indeed not context-free. Okay? So the explanation for this one is pretty similar to the explanation in case 2 of example 1. So yeah, it's pretty straightforward. And finally, we have our last example. Let's show that the language 0M, where M is a perfect square, is not context-free. Okay, it's not context-free using the bumping lemma. So first, we'll assume again that M is a perfect square. So let's assume that this language is context-free. So therefore, the pumping lemma should hold true for this language. Now, the sufficiently long string that we'll use is z is equal to O n squared, and this is valid because, well, it's part of the language because it has a squared. The length of the number of zeros is a perfect square, and the length is greater than n because n squared is greater than n greater than or equal to n for n greater than or equal to 1. Okay? So, what will happen? So we can write z as UVWXY, where the two conditions are met, right? So we know that the length of z, or the length of the string, is n squared because we have n squared zeros. Okay? And the length of UVWXY is also n squared because UVWXY is just the z. So now, let's take the minimum case for v and x. V and x could be at least 1, right? So the minimum case for the length of vx is 1. Now, why are we interested in vx? It's because these are the ones that we will pump, right? V and x. Okay, remember, we pump v and x in tandem. So the minimum case for vx is 1 because in here, length of vx could be greater than or equal to 1. So the minimum is 1. Now, how about the maximum length? So the maximum length of vx could be n, and that is if w here is epsilon, because the length of vwx cannot exceed n. Okay, so if w is epsilon, then vx could be n in length. Okay, now if we pump up vx, it would become uv squared wx squared y. That should be part of the language, right? But uv squared wx squared y is basically just what? uv squared wx squared y is just uvv wxx and y, because you just repeated the v and the x twice. Okay, so the length of uv squared wx squared y should be equal to the length of uv wxy plus the additional v that you added and the additional x that you added. So plus vx. Okay, so let's write that here. Length of uv squared wx squared y is equal to uv wxy plus length of vx. Okay, let me erase this one first. Okay, so let's go to the next one. So in the minimum case for vx is equal to 1, that means that one of v and x is a 0 and the other is epsilon, right? Because, well, why is it a 0? Because, well, the z is just O of n squared. It's all zeros, right? But if the length of v and x is just 1, so that means that only one of v and x is a 0. The other has to be epsilon. So that means that if you pump up v and x, you only add 1 0. So regardless of it was, maybe if it was v is equal to 0 and x was epsilon, or v was epsilon and x was 0, if you pump up v squared x squared, this would become, v squared would become double O, so you added 1 0, whereas x would still be epsilon, right? And then here it would still be epsilon, and then x squared would become 0 0. So you added 1 more 0. So in both cases, you'd really just add 1 more 0 to the string. Okay, so therefore the length of this pumped up string is just the original plus the vx, which is just 1, right? So it was n squared, because the length of uvwxy is n squared, right? We have that one here, plus 1 because of the 1 0 that you had. Okay, now how about in the maximum case? What if it's n? Vx is n. So vx has a total of n zeros, because, well, everything is a 0 anyway. So that means that you're adding n zeros when you pump up vx. Okay, v squared x squared. So that means that the length of this, the length of vx here is just n. Okay, so you add n squared plus n, because the length of this is n squared because you have n squared zeros, and then the length of Vx here is n because you're adding n zeros because that is the maximum total. So therefore, we could set a range for this one. So at the minimum, it would have the length n squared plus 1, and at the maximum, it would have the length n squared plus n. So in general, it's between n squared plus 1 and n squared plus n if you have this pumped up string, right? So this is the inequality. But we know that n squared is less than n squared plus 1, right? Because of the plus 1 here. And then n squared plus n is less than n squared plus 2n plus 1. Why is that? Because, well, of course, this one is just n, this is 2n, and then you have the plus 1. So of course this will win out. But what is n squared plus 2n plus 1? This is just n plus 1 squared, right? So if we chain this one together like this one, so we could have less than, so n squared is less than n squared plus 1, and then here n squared plus n is less than n plus 1 quantity squared. Okay, so if you remove this 2, we could just have n squared is less than the length of u v squared y wx squared y, and then less than n plus 1 squared. Okay, so you have that one. So n squared is less than the length of the pumped up string is less than n plus 1 quantity squared. Now, why are we showing this? Well, the reason why is because supposedly the pumped up string has to be part of the language, right? And the language contains strings with a number of zeros, wherein the number of zeros is a perfect square, right? But the pumped up string here, the length of the pumped up string is between two perfect squares. You have the n squared and the n plus 1 quantity squared. So these are two succeeding perfect squares, right? N squared is a perfect square, n plus 1 quantity squared is a perfect square. So therefore, this one cannot be a perfect square. Does that make sense? Because, for example, if let's say we have let's say we have 3 squared and 4 squared. Okay, so the numbers in between 3 squared and 4 squared cannot be perfect squares, right? If you have 9 and 16, there are no perfect squares in between them, right? So in the same reason, if you have n squared here and n plus 1 quantity squared here, then everything in between cannot be a perfect square. A perfect square. Okay? So what does that prove? Well, since it's not a perfect square, the length of the pumped string is between two perfect squares. That means that it's not a perfect square. And that means it's not part of the language, because the language only takes number of zeros where it's a perfect square. Okay, so this one is a contradiction, and so for all possible values of Vx, we arrived at a contradiction because we looked at the minimum possible and the maximum possible, so everything in between will also be invalid. Okay, so because it arrived at a contradiction, then we have proved that the language OM, where M is a perfect square, is not context-free. Okay, so that is how you use the pumping lemma to prove languages to be not context-free. Okay, so that's it for this video. To review, we discussed the decision properties for CFL. So we had the membership, the emptiness, and the infiniteness. So for membership, then you have the polynomial time algorithms for parsing. Then for emptiness, you just check the CFG if the start symbol does not derive any terminal strings. Then for infiniteness, you draw the graph of the CFG and check if there are cycles, right? Then for closure properties, you have the union, concatenation, closure, reversal, and homomorphism. So for union, you just create the for this one, you just had the SG or SH. And then for concatenation, you had the SG, SH. And for Kleene Closure, it was like epsilon or SGS, something like that. And for reversal, we just reverse everything. So if it was 0, S1, 0, 1, this becomes becomes 1 SO or 1O, something like that. And for homomorphism, then you just apply the homomorphism. So if it was H of O is equal to AB, and then H of 1 is equal to C, then this becomes ABSC or ABC, something like that, right? So all of them produced a CFG, and so that makes them context-free as well. And then, of course, the pumping lemma for context-free languages. So for all context-free languages, there's an integer n greater than or equal to 1, such that for every string that's sufficiently long, we can divide z into 5 parts, u, v, w, x, y, such that vwx does not exceed n in length, and vx has to be at least 1, so both cannot be empty. And then we can pump up v and x for all k greater than or equal to 0, and the pumped up string can still be part of the language, right? So we use this to prove languages to be non-context free. Okay, so that actually ends our topics for context-free languages and pushdown automata. So this is the end of our topics for the second long exam, and yeah, so the next we will have our second long exam, and then in the next weeks we will have the final set of topics, which would be about Turing machines and recursively enumerable languages. So we'll also talk about Turing machine extensions, and then we'll dabble a little bit on theoretical computer science, talking about undecidability, intractability, and the P versus NP problem. So that would be all in the last part of our ComSci 141 course. And so yeah, that's it for now. And if you have any questions, please don't hesitate to ask, and I will see you in the next video.